Hello everyone again, and welcome to this particular video where in here we're going to be diving into organic chemistry level 3, which involves a little bit of metal catalytic reaction, or people can call it organometallic catalytic reactions. And this is one that you need to be familiar with, involving Heck reaction and how to determine or predict products when given a reactant or series of reactants, and you need to be able to identify what each reactant does in a specific reaction step and how to highlight the mechanisms that are required in order for you to achieve the final product and also regenerate the catalyst in here. So in there we see this particular diagram where we have the little bit of oceanic reactants and we have the gold color catalyst right there, which in this case mainly deal with palladium. Palladium is quite fascinating in terms of how rich it is in alternating from one oxidation number to the other in order for it to effectively be reused in other organometallic catalytic reactions. So in here we're going to look at in the part 2 dealing with big idea question, which involves giving a mild condition reaction where we have this reactant and the TF is known to be represented as trifluoromethyl sulfate, and this particular compound in general, the red compound, is known to be a form of an organohalide, and this will be nice to recognize because once you dive into the main reaction you should know which one starts first or which one ends up later, and this is going to be combined with this particular reactant here, which actually has a little bit of a double bond, which is an alkene, and also we have a level of carboxylic group and also an amine group around there, and this is under the influence of various reactants or reagents where we have 10 more percent of palladium, and this is combined with toluene, which is a form in here of a phosphine in here, and this phosphine is combined as well with a base and solvent. So in here our goal is to determine the product, which is a major product, that series of products that will be produced during this reaction. But how can you be able to favor a specific major product? And this comes into play by knowing the key idea of the Heck reaction, and the key facts. One comes from knowing that this reaction favors one isomer compared to the other, and on our next videos we will dive more into the possible isomer that is favorable and at what conditions that is actually enhanced. Now the next thing is that there is a double bond that is polarized by the electron withdrawing group that forms the sigma bonds at the other end of alkene. So this is one thing you need to recognize while developing your mechanism and being aware of that. And finally here is that the catalyst, in this case metal palladium, is added as palladium 2, not palladium 0. So you start off with palladium 0 and then it transforms into palladium 2 where it is active in the circle, and then once you get back into the original state, which is palladium 0, you perform a form of a reductive elimination reaction. So that will come into play mainly on our next video, but for this video we're just going to look at the big idea on the Heck reaction. So let's start off with what we know in this case to be the solution, which is developing the mechanism. So we have our reactants, the key reactants that we need to combine in order for we to create our final major product and the one isomer that is favorable. And we have here the supporting reactants that actually creates that conditions that is suitable for we to generate our major product. So the mechanism here is, first you start off with your catalyst, which is your palladium, and this palladium has the ligands in here. The ligands kind of creates this particular oxidation number in here, starting off with 0, which means that it has 14 electrons in there. And what happens is that once you introduce your specific reactant, which you notice to be an organohalide, that is what you always start off with. Your organohalide in this case will be introduced, and once that is introduced, then we have a form of electron transfer where our palladium attacks that specific carbon, that is a pi carbon, and this is going to lead to the breaking of the sigma bond, that leads to the forming of a sigma bond with that palladium. So therefore we have a good leaving group attached to palladium, and the ring that has the double bond is actually attached to the same catalyst, and this actually leads to the next step, which is a carbometallation. And this form or step introduces us to the next reactant, which in this case is the carboxylamine that we have with the pi. And what you see is that the pi actually forms a form of interaction with palladium, and this pi interaction with palladium then leads us to a form of a cyclic, I would say SN2 type reaction, where the pi forms a sigma bond with the palladium, and the other bond is broken and forms a sigma bond with that particular alpha, I'll call it carbon, on that alkene. Therefore, in this case, we have our product, which is in this case the forming of just one bond attached to palladium, but we have our intermediate product where we need to perform one final step, and this final step involves a beta-hydrogen that is going to be involved in the breaking off of our final product, and our final product to have a new pi bond. So therefore this next step, which is called a beta-hydride elimination, actually involves the beta hydrogen to form a sigma bond with the palladium, while the sigma bond that attaches palladium to that specific chain is going to be broken off to form a new pi bond. And this pi bond that is created then leads us to the formation of our final product that leaves, and this is our major product, that is a form of a cis, not a trans product. And this is highly influenced mainly by not only the steric hindrance that may contribute to the formation of the final product, but also looking at it in terms of the energetics or activation energy that is suitable for the formation of this final product. So once we have that, then we have our other step, which involves our palladium, which is still having a 16 electrons, which is active, and a oxidation number of +2. So therefore in this case, to bring it back to the 14 electron, we have to perform a method which is called reductive elimination. And at this step, what we can do is to use our base. In this case, we use potassium carbonate, and potassium carbonate here will have its dissociated form, which is carbonate with 2 minus, and what this does is it picks up the hydrogen, and the hydrogen sigma bond is broken off, which forms the 2 electron lone pair into palladium, while palladium cleaves its bond with the OTF, and this actually leaves, and this leads to the formation of our living soluble, I would say, product that we don't really care about honestly, and we regenerate mainly our inactive palladium in that particular case right there, which is a 14 electron palladium 0 that we started from. So take note here that the major product in this particular reaction actually has a 77% yield, which is really a huge amount considering how much we actually restricted this reaction to the specific reagents that are actually involved in that conditions right there. So on our next video, we're going to focus on the beta-hydride elimination that leads to the major product, that tells us why that major product is actually generated. And also our next video will look at the types of base that are used to regenerate our palladium 0 coming from palladium 2. So that's about it for this particular video. Please hope you're able to understand this. Hit a comment down below and let me hear your thoughts. By that way I can talk to you later. Don't forget to subscribe. See you all soon. Stay smart and believe in yourselves.